Next topic, Wronskian. Let y1 and y2 be two solutions of the second order differential equation y double dash plus p of x into y dash plus q of x into y equal to 0. Then Wronskian of y1 and y2 is denoted by like this: w of y1 y2. It is defined to be the determinant value of y1 y2. The first row is occupied by the solutions y1 and y2. The second row will be its derivative y1 dash and y2 dash. Using the determinant expansion, we could find the values of the Wronskian values of y1 and y2 like this. Okay. Next, let's see how we can check the linear independence or dependence of the two solutions. Using these two theorem will help us to find whether the solutions are linearly independent or dependent. Two solutions y1 and y2. Let y1 and y2 be the two solutions of the differential equation y double dash plus p of x into y dash plus q of x into y equal to 0. And these solutions y1 and y2 are linearly independent if the Wronskian value is non-zero. Okay. Also, the two solutions y1 y2 of the differential equation is linearly dependent if the Wronskian value is 0. So two values of a differential equation is non-zero, they will become linearly independent, and if it is 0 then it is linearly dependent. Okay, now let us see some problems dealing with the linearly dependent and linearly independent and dependent properties. First problem, show that the solution of y double dash minus 2 y dash plus y equal to 0 are linearly independent. We need to check whether these solutions of this differential equation are linearly independent or not. First, find the solution of this differential equation. Using the second order differential equation solving method, we will find the two solutions of this differential equation as like this: replacing the y double dash by d square y and y dash by dy, and taking common y as common, taking y common outside, and the auxiliary equation can be formed by replacing capital D by lambda. So the auxiliary equation will be lambda square minus 2 lambda plus 1 equal to 0. Using factorization method, we could find the two values of this quadratic equation as lambda 1 equal to 1 and lambda 2 equal to 1. These two roots are real numbers. At the same time, they are same real numbers. So the case 2 is arising here. So the general solution format will be y equal to c1 plus c2 x into e raised to lambda x. Now replace the value of lambda as 1. We will get the general solution as c1 plus c2 x into e raised to x. So while expanding, we can return the general solution also in the format y equal to c1 e raised to x plus c2 x e raised to x. Now we got two solutions, y1 as e raised to x and y2 as x e raised to x. Now we need to check whether these two solutions are linearly independent or not. For this, we will find the Wronskian values of these two solutions as like this. First row will be the values of y1 and y2, so replacing it by e raised to x and x e raised to x. Then the next row will be its derivative, so derivative of e raised to x is e raised to x, and the derivative of x e raised to x. Derivative of x e raised to x, we will use product rule. First function to derivative of the second function plus second function to derivative of the first function. So x e raised to x plus e raised to x. Now using determinant expansion and cancel the similar terms, we will get the value as e raised to x, which is a non-zero value. Hence the Wronskian of the solutions is non-zero. Hence we can say that the solutions y1 and y2 are linearly independent. This is the procedure for checking a linearly independence of two solutions of the given differential equation using Wronskian method. Now let's find the Wronskian of the given bases and show that they are linearly independent. Two more questions for checking the linearly independence of the two solutions. Here the solutions is already given. We have to just check whether these solutions are linearly independent or not. For that, just enough to find the Wronskian value of the given solutions. The first problem, x raised to 4, x raised to log x. So find the Wronskian value of these two solutions. Using determinant expansion, we could find the solutions. Replace y1 as x raised to 4 and y2 as x raised to 4 log x. Then the next row will be its derivative. X raised to 4 derivative is 4x cube, and the derivative of x raised to 4 log x, find it using product rule of differentiation. Will get the value as x cube into 1 plus 4 log x. Using determinant expansion, we will get the value as x raised to 7, which is a non-zero value. So we can say that this is a linearly independent solutions. Next problem, the first row will be the values of y1 and y2, 1 and e raised to x. Next row will be its derivatives. So using determinant expansion, the value is e raised to x, which is again a non-zero value. So these two solutions, 1 and e raised to x, are linearly independent. In the previous videos, we have deal with the homogeneous linear differential equations with a constant coefficient. Now we are looking to non-homogeneous linear differential equations with a constant coefficient. How we can solve a non-homogeneous linear equation with constant coefficient. So the standard form of a non-homogeneous linear differential equation be y double dash plus a y dash plus by equal to r of x. Now replace the y double dash by d square y and y dash by dy. Then taking y as common outside, then we'll get d square plus ad plus b of y equal to r of x. And the solution part will contains two parts, complementary function and particular integral. Now let us see what is complementary function and particular integral. Complementary function actually, which is the solution of this homogeneous equation. We are dealing with the non-homogeneous equation with constant coefficient y double dash plus a y dash plus by equal to r of x. So just take the homogeneous part of this non-homogeneous equation. So the right side will be 0. Okay, now the solution of this homogeneous equation will be the complementary function. Okay, next particular integral. Particular integral will be the solution of this homogeneous equation. After that, adding to these two parts, particular integral and a complementary function, we will get together the solution of the given non-homogeneous differential equation. So the solution part will be the sum of complementary function and particular integral. It can be also denoted as, the complementary function can be denoted as yc and particular integral can be denoted as yp. So the general solution will be the sum of yc and yp. Now there are two methods for finding the particular integral. For the first method is method of variation of parameters. For using the method of variation of parameters, let's see how we can find the particular integral using this method of variation of parameters. For this, I am considering the non-homogeneous equation y double dash plus a y dash plus by equal to r of x, and let yc be the using the procedure of homogeneous method, differential equation solving method, find the complementary function. So I am considering the homogeneous part of this given non-homogeneous equation and finding its solution as yc equal to c1 y1 plus c2 y2. Next we need to find the particular integral. The particular integral can be found by using this integral equation. Replace the terms y1 y2 from the complementary function, and r of x will be the right side of the non-homogeneous equation, and w will be the Wronskian value of the two solutions given. The two solution we have derived from the complementary function. So from the complementary function, identify the y1 and y2 solutions and then find its Wronskian value. Just replace it here as w, and you solving this integral equation will get the particular integral value. After that, the sum of the yc and yp will be the sum of the general solution. Now let us see how we can find or how we can solve a non-homogeneous differential equation. Okay, so applying method of variation of parameters, solve this differential equation. So first method is to find the complementary function. So for finding the complementary function, just find the just consider the homogeneous part of the given non-homogeneous equation. So the homogeneous part means the right side taking as 0. So we get d square y by dx square plus 4y equal to 0. Now I am replacing the d square y by dx square as d square y, and taking y as outside we will get d square plus 4 of y equal to 0. So the auxiliary equation will be lambda square plus 4 equal to 0. Thus the roots of lambda will be plus or minus 2y. It's a complex roots. So the case 3 is arising here. So the general solution format is yc equal to e raised to alpha x c1 cos beta x plus c2 sin beta x. Here the value of alpha is 0 and value of beta is 2. So the complementary function value will be e raised to 0x c1 cos 2x plus c2 sin 2x. And also we know that e raised to 0 is 1. So the complementary function can be written as c1 cos 2x plus c2 sin 2x. Now this is of the form yc equal to c1 y1 plus c2 y2. So the value of y1 is cos 2x and y2 is sin 2x. Now find the Wronskian of y1 and y2 like this, replacing the first row by y1 y2 and the second row by its derivative. Then find the determinant value of these functions. We will get it as 2. Okay, now we need to find the particular integral using the method of variation of parameters. The integral equation is given as like this. So replacing y1 as cos 2x, y2 as sin 2x, r of x will be the right hand side of the given non-homogeneous equation. The right hand side of the non-homogeneous equation is given as 4 sec square x, which is the value of r of x. So replacing r of x as 4 sec square 2x, and the Wronskian value we got it as 2. So taking w as 2. Now replacing all these values here, we could solve the differential equation like this. Now I am deleting 2 in both integral parts and writing sec square 2x. The sec square 2x can be written as 1 by cos square 2x. Okay, this can be written as 1 by cos 2x into 1 by cos 2x. So sin 2x into 1 by cos 2x, this is written as like this, and again 1 by cos 2x is written as sec 2x. Okay, next again here we have cos 2x into sec square 2x. Sec square 2x can be written as cos square 2x. So we can delete 1 cos 2x and from this square we can delete 1. So we get 1 by cos 2x, which is sec 2x. Okay, now sin by cos 2x is tan 2x, 1 by cos 2x is sec 2x, and here remaining is sec 2x. Using the direct integral formulas, we can find the integral value of integral tan x sec x. Integral tan x sec x is sec x. So here it will be integral tan 2x into sec 2. So it is sec 2x by its derivative. It's 2x into derivative of 2x is 2. So dividing it by 2 plus 2 into sin 2x. Integral sec 2x will be log sec 2x plus tan 2x by its derivative 2x. I will explain once more. Integral tan x sec x is sec x. So integral tan 2x into sec 2x will be sec 2x by derivative of 2x. It is 2. That's why we got it as sec 2x by 2. Now again, integral sec x dx is log sec x plus tan x. So sec 2x will be log of sec 2x plus tan 2x by its derivative 2. Derivative of 2x is 2. Now simplifying all these terms, we will get cos 2x into sec 2x. Sec 2x can be written as 1 by cos 2x. So we can cancel both these terms. We will get minus 1, and 2 can also be cancelled here, and the particular integral value will be minus 1 plus sin 2x into log of sec 2x plus tan 2x. Now the general solution will be the sum of the yc and yp. Yc is got as c1 cos 2x plus c2 sin 2x minus the yp part minus 1 sin 2x plus log into sec 2x plus tan 2x. Thank you. Next problem. By method of variation of parameters, solve the differential equation d square y by dx square plus y equal to cosec x. This is a non-homogeneous equation. So the solution contains two parts, the complementary function and the particular integral. So first find the complementary function. So just consider the homogeneous part of this given differential equation, y double dash plus y equal to 0. Now replace the y double dash by d square y and taking y as common outside and replacing the capital D by lambda, will get the auxiliary equation as lambda square plus 1 equal to 0. So its roots are plus or minus I. Here the roots are complex numbers. So the general solution will be the format by applying by case 3. General solution format will be e raised to alpha x into c1 cos beta x plus c2 sin beta x. Here the value of alpha is 0 and beta is 1. So we will get the solution the complementary function as c1 cos x plus c2 sin x, since the exponential raised to 0 value is 1. So choosing, here we are choosing this term cos x as the y1 value and sin x as the y2. Two solutions, y1 and y2. Then find the Wronskian value of y1 and y2 using the determinant expansion. The first row is the values of y1 and y2 cos x and sin x. Second row is its derivative minus sin x cos x. Using the determinant expansion we get cos square x plus sin square x. The value is 1. So the Wronskian value here it is 1. Now we can find the particular integral. The integral equation is minus y1 integral y2 r of x by w dx plus y2 into integral y1 r of x by Wronskian w dx. Here we have the value of y1 is cos x, value of y2 is sin x and r of x is cosec x, which is the right hand side value of the given question. It is cosec x. Okay, and w is the Wronskian value that we have recently found the value of Wronskian as 1. So replacing all these values in the integral equation, and now we are going to solving it. Sin x into cosec x. Cosec x means 1 by sin x. So we can solve sin x into 1 by sin x. The value will be 1. So integral 1 dx. Also cosec x into sin x. This cosec x can be written as 1 by sin x. So cos by sin, the value is cot. Then integral dx is x and integral cot x is log sin x. So we get the particular integral value as minus x cos x plus sin x into log modulus sin x. So the general solution will be the sum of complementary function and particular integral. So the general solution for the given non-homogeneous equation is, differential equation is y equal to c1 cos x plus c2 sin x minus x cos x plus sin x into log modulus sin x. This is a procedure for solving a non-homogeneous linear differential equation with a constant coefficient using the method of variation of parameters. Our next problem, using the same method of variation of parameters, solve this homogeneous linear differential equation with constant coefficients y double dash minus 2y dash plus 2y equal to e raised to x into tan x. So the right hand side value means the r of x value is e raised to x into tan x. Next we need to find the complementary function. So we are considering the homogeneous part of this differential equation as y double dash minus 2y dash plus 2y equal to 0. Now replacing the y double dash by d square y and y dash by dy and taking y as common outside and replacing the capital D by lambda. The procedure is same as above. So the auxiliary equation will be lambda square minus 2 lambda plus 2 equal to 0. Hence the roots are 1 plus or minus I. Here it is complex roots. So the value of alpha is 1 and beta is 1. So the general solution will be of the form e raised to x into C1, general solution not, actually it is complementary function. Complementary function value is e raised to x into C1 cos x plus C2 sin x. This can be also written as by expanding the brackets C1 e raised to x into cos x plus C2 e raised to sin x. So the value of y1 is e raised to cos x, e raised to x into cos x, and the value of y2 is e raised to x into sin x. Then find its Wronskian value. Wronskian value by expanding the first row is the values y1 and y2 here, and its derivative included in the second row, and using determinant expansion some of the terms are missing, cancelling here. E raised to x into e raised to x is e raised to 2x, so we can cancel these two terms, and combining the rest of the two terms and taking e raised to 2x as outside, we'll get cos square x plus sin square x. Its value is 1, so we'll get the Wronskian value as e raised to 2x. Okay, next we can find the particular integral using this integral formula. So replacing y1 as e raised to x cos x and y2 as e raised to x sin x. R of x is given in the question. From the right hand side, we will get r of x values is e raised to x into tan x, and Wronskian value we got it as e raised to 2x. So replacing all the values in this integral equation, now we can simplify the terms by cancelling some of the terms. Here we have in the numerator e raised to x into e raised to x, so the value is e raised to 2x. We can cancel it with the denominator value, so we'll get rest of the values as integral sin x into tan x. Similarly, we can cancel the e raised to x into e raised to x by e raised to 2x. Now I am writing this tan x as sin x by cos x, and again here also replacing tan as sin by cos. Then sin x into sin x is sin square x. Also I am cancelling these two terms, cos x into cos x, will get integral sin x. Now for simplifying the integrating these terms, we need some simplifications further. So I am replacing sin square x by 1 minus cos square x. Since the value of sin square x plus cos square x is 1, so we get sin square x is 1 minus cos square x. Through that result, so I am replacing sin square x by 1 minus cos square x, and separating the denominator, we'll get 1 by cos x minus cos square x by cos square x, and cancelling the cos square x from the numerator and denominator, I'll get cos x, and also 1 by cos x is sec x. We have formula for the integral sec x and cos x, so we can directly integrate all these terms. So we get integral sec x is log sec x plus tan x, integral cos x is sin x, also integral sin x is minus cos x, and expanding these brackets, some of the terms will cancel, and the particular integral is minus e raised to x into cos x into log of sec x plus tan x. So the general solution for the given non-homogeneous differential equation will be the sum of complementary function and particular integral. So its general solution is c1 e raised to x cos x plus c2 e raised to x sin x minus e raised to x into cos x into log of sec x plus tan x. It will be the general solution for the given non-homogeneous linear differential equation. Our next problem. Solve the differential equation d square y by dx square plus y equal to x into sin x. So the right hand side value r of x equal to x sin x. Okay, first find the complementary function. So I am considering the homogeneous part, d square y by dx square plus y equal to 0. Replacing d square y by dx square as d square y, taking y as common outside, we will get d square plus 1 of y equal to 0, and I am replacing d by lambda to get the auxiliary equation. So the auxiliary equation is lambda square plus 1 equal to 0. The roots of this quadratic equation are plus or minus I, complex roots. So the case 3 is arising here. So the value is e raised to, this is of the form alpha plus or minus I beta. So the general solution format will be e raised to alpha x into c1 cos beta x plus c2 sin beta x. So here the value of alpha is 0 and beta is 1. So we'll get yc equal to, that is complementary function value as c1 cos x plus c2 sin x. Next we can find the particular integral. For that first we need to find the Wronskian value of these two solutions. From the complementary function we will get the value of y1 is cos x and the value of y2 is sin x. Then find the Wronskian value using the determinant expansion. First row is the y1 and y2, second row will be its first derivatives minus sin x and derivative of sin x is cos x. Using the determinant expansion we will get the Wronskian value as 1. Next, using the integral equation formula, we can we could find the particular integral value. So replacing y1 as cos x, y2 as sin x, r of x is the right hand side of the given non-homogeneous equation. It is x into sin x. Wronskian value is 1 here, and similarly substitute all these values in the second part. Now we are combining all the terms. X sin x into sin x is sin square x. Also just rearranging these terms as x into sin x into cos x. Now for finding the integral value of these terms we need some simplification. For this I am substituting the value of sin square x as 1 minus cos 2x by 2. Since we have the trigonometric formula cos 2x equal to 1 minus 2 sin square x. So the value of sin square x will be 1 minus cos 2x by 2. Also here we have 3 terms of x, so we need to apply product rule. For furthermore simplification we are substituting sin x into cos x as sin 2x by 2, since sin 2x equal to 2 sin x into cos x, so the value of sin x cos x will be sin 2x by 2. Now apply, I am taking the 2 from the denominators on both sides to be the outside of integral. Since it is a constant coefficient, this can be also written as in this form. Now apply the integral values. X, integral of x is x by 2, and the integral of x cos x we need to apply the product rule of integration. So first function integral of the second function minus integral of derivative of first into integral of the second function. So using this result find the integral value product rule. We are applying the product rule here, or further we can apply another method using u dash v1 u v1 minus u dash v2. This can be also applied. V1 means here u is x and v is cos x. So u and its first derivative, v1 means first integral of the cos x, v2 means second integral of the cos x. So we get x into v1 first integral of cos x. Actually it is cos 2x. So integral of cos 2x is sin 2x by 2x, derivative of 2x is 2, minus u dash, derivative of x is 1, into derivative integral of the second integral of cos 2x. So integrating sin 2x by 2, again with respect to x we get minus cos 2x by, already here we have 2, then again derivative of 2x is derivative of the derivative of 2x is 2, so 2 into 2 we get 4. So the integral of x cos 2x dx will be x into sin 2x by 2 plus cos 2x by 4. That is actually we got here. Okay. Similarly find the integral value of x sin 2x. Here we could find it using, here take x u as x and v as sin 2x. So integral, so first function x into v1 sin 2x, integral of sin 2x is minus cos 2x by 2, derivative of 2x, minus derivative of x is 1 into integral of the minus cos 2x by 2 minus sin 2x by 4. So we get x into minus cos 2x by 2, minus of minus it will be plus. Okay. Now I am just applying minus to the minus 2 common as to the brackets, and opening rearranging we will get the value of particular integral as like this. So the general solution will be the sum of this particular integral and the complementary function.